Psychologists gave us cognitive dissonance, physicists dropped the holographic principle, and biologists hit us with epigenetics. All of these theories, in some way or form, ripped holes in the old ways of thinking and rebuilt how we see everything, atoms to identity. I'm Mike with List 25, and these are 25 groundbreaking scientific theories explained. Two things real quick though. First of all, before we begin, don't forget to give that algorithm a nudge. Like, share, comment, subscribe, hit that notification bell so you don't miss out on any of the content. And two, my voice is still a little shot from the Tampa Bay Buccaneers game the other day, so sorry, hasn't come back yet. With that being said, let's get sciencey. 25. Cognitive dissonance. If you've ever done something bad but explained it away, you're familiar with this one. This famous psychological theory was coined in 1957 by psychologist Leon Festinger to describe the discomfort we feel when our actions do not match our beliefs. For example, let's say you're a smoker. Smokers know cigarettes are bad for them, but they light up anyway. Same with overeating, or spending too much money, or staying in a relationship that makes no sense. The behavior stays, but the brain does everything it can to help you make peace with it. You tell yourself stories like, my grandpa smoked and lived to 90, or I needed that new phone, it was on sale. Cognitive dissonance explains why we defend bad decisions, stick to shaky political perspectives, or stay in tough relationships. We're not always truth seekers. Sometimes we're comfort seekers. 24. String theory. What is everything really made of? Instead of treating the universe as built from point-like particles, string theory says the fundamental building blocks are tiny vibrating strings of energy. Each vibration mode creates what we see as different particles. One pattern might be an electron, another a photon, and so on. One of string theory's craziest predictions is that extra dimensions must exist beyond the three we move through and the one we call time. These hidden dimensions would be curled up so small we can't detect them, but they're needed for the math to work. Another major promise is that string theory naturally includes gravity at the quantum level, something most other theories fail to do. That makes it a strong candidate for a theory of everything. 23. Quantum gravity. Right now, physics runs on two different playbooks that do not get along. Einstein's relativity theory explains gravity and the big stuff in the universe, while quantum mechanics explains the tiny world of particles. Both are brilliant on their own, but when you try to mix them, the math falls apart. When we look at what we know about the happenings inside of black holes or at the very beginning of the universe, neither theory can tell us the full story. That is where quantum gravity comes in. It's not one finished theory, but a quest to link the two together. String theory tries to do it with vibrating strings and extra dimensions. Loop quantum gravity tries a different route, breaking space and time into tiny building blocks. Either way, the idea is that space-time itself has a hidden quantum structure, not the smooth fabric that Einstein imagined. 22. Endosymbiosis. This theory is part of the broader story of evolution, but it doesn't argue about where life began. Instead, it tackles how life became more complex. Endosymbiosis suggests that billions of years ago, a simple cell swallowed another one, and instead of destroying it, the two worked out a partnership. The guest cell provided energy while the host cell gave it food and safety. That unlikely alliance is why you have mitochondria today, the little power plants inside your cells. In plants, a second merger brought in chloroplasts, which transform sunlight into energy. Both mitochondria and chloroplasts still carry their own bits of DNA, proof they were once independent organisms. When the theory was first proposed in the 60s by biologist Lynn Margulies, it wasn't very popular. But as we learned more about the structure of DNA, it became harder to deny. Mitochondria and chloroplasts clearly carry bacterial signatures, so she was right after all. 21. Exoplanets and the Drake equation. For most of our history, the Earth's brightest minds have wondered if the stars we see out there had planets of their own, like ours. Now we know the truth. Thanks to telescopes like Kepler and TESS, thousands of these exoplanets have been found, including Earth-sized ones sitting in their star's habitable zone where water could exist. This ties directly into the Drake equation, created in 1961 by astronomer Frank Drake. His theory wasn't so much a single prediction, but more a formula that multiplies things like how many stars are born, how many have planets, how many of those planets could support life, and how many civilizations might actually broadcast their existence. In the 60s, most of those numbers were wild guesses. Today, we can fill in some blanks with real data. The galaxy is packed with planets. Whether life is out there is still an open question, but for the first time, we can study it scientifically instead of just wondering. 20. The holographic principle. There's a distinct possibility that our 3D universe might actually be described by information on a 2D surface, the way a flat hologram projects a 3D image. It all started with black holes. In the 70s, Jacob Bekenstein and Stephen Hawking showed that the amount of information in a black hole depends on the surface area of its event horizon, not its volume. That was strange. It was like saying everything inside could be recorded on its outer shell. Physicists later expanded this to the whole universe. The suggestion is that everything happening in space could be fully captured on a surrounding boundary. In string theory, this even plays out mathematically in models where a world with gravity and a higher number of dimensions has an exact twin living on a lower dimensional surface. We don't experience reality as flat, but the math suggests it might be written that way underneath it all. 19. Deep learning, neural networks, and AI. If you've ever talked to a voice assistant, let your phone tag friends in photos, or used a translation app, you've already seen deep learning at work, right, Gemini?
Correct. Voice assistants, photo tagging, and translation apps are all common examples of deep learning applications.
The idea is simple. Instead of programming a computer step by step, you give it a model inspired by the human brain and let it learn from examples. These models are called neural networks. They're built from layers of neurons that pass signals to one another. The more layers you stack, the deeper the network becomes. Early layers might pick up on simple details like edges or colors in a picture, while later layers can recognize a face, a cat, or a stop sign. The theory is that a big enough network, given enough data, can learn almost any pattern. That's why deep learning now powers self-driving cars, medical imaging, game-playing AIs, and chatbots. It's literally computers spotting patterns at a scale no human brain could handle. Who's smarter, you or me?
That's a fun question. I can't really compare intelligence with a person because we're fundamentally different. I can process vast amounts of data very quickly, perform complex calculations. You, on the other hand, possess qualities like creativity, emotional intelligence, and the ability to set goals and make judgments based on life experience, which I don't have.
18. The human microbiome. You are never really alone. Right now, you have trillions of microbes living inside of you, especially in your gut. And together they make up what scientists call the human microbiome. These microbes act almost like an extra organ, helping you to digest food, produce vitamins, and train your immune system. What really surprised scientists was the discovery of a direct gut-brain link. Some of these microbes produce the same chemicals your brain uses to regulate mood. So researchers are now exploring how this could relate to depression, autism, or even Parkinson's. Your microbiome also shapes things like weight, allergies, and autoimmune conditions. Change your diet, and you change your microbes. Disturb them with antibiotics, and you might feel the effects in unexpected ways. In short, your gut controls your mind as much as the conscious decisions you make every day. So your health really is a whole body-mind relationship in every way. 17. Epigenetics. The theory of epigenetics says your DNA is not a fixed density. Instead, it can be switched on or off by small chemical tags added through life experiences like stress, diet, or exposure to toxins. These tags attach to your DNA, or the proteins it coils around, changing how genes are expressed without altering the genetic code itself. That's why identical twins who share the same DNA can grow up to have different health problems or traits. Some of the most striking evidence for epigenetics comes from real-world trauma. Studies of Holocaust survivors found that their children and even grandchildren carried epigenetic changes linked to stress and anxiety. Another famous case came from the Dutch hunger winter of 1944-45, where the children people conceived during the famine were more likely to face obesity, diabetes, and heart disease later in life, and some of those effects carried into the next generations. The core idea is simple. DNA is the blueprint, but epigenetics decides which parts are read. Your environment leaves molecular marks that can shape not just your life, but the lives of those who come after you. 16. Information theory. Every text you've sent, every song you've streamed, and every video you have watched has Claude Shannon to thank. In 1948, he came up with a way to treat information itself as something measurable. His unit was the bit, short for binary digit, and it became the building block of the digital world. The genius of Shannon's idea was that anything, words, pictures, sounds, can be broken down into bits of zeros and ones. He also found that the amount of information depends on surprise. A coin toss gives you 1 bit because the outcome is uncertain. A guaranteed heads gives you 0 information. Shannon also nailed the limits of communication. He showed that there's a maximum speed you can push data through a noisy channel without errors, and engineers have spent decades inventing codes that get as close as possible to that ceiling. 15. Quantum computing. If regular computers are calculators, quantum computers are more like guessing every answer at once and then narrowing it down. A normal computer runs on bits, tiny switches that are either a 0 or a 1, as I just mentioned. Quantum computers use qubits, which can be ones and zeros at the same time until you measure them. Link a bunch of qubits together and suddenly you have a system that can juggle possibilities in parallel instead of one after the other. That makes certain problems way easier to crack. Encryption, for example, could be broken by a quantum computer in minutes, code that would take a normal computer longer than the age of the universe to solve. They can also simulate molecules, which can speed up drug discoveries or crunch massive optimization problems in logistics and finance. The catch is, qubits are fragile and collapse easily. But the theory is sound, and as prototypes improve, quantum computing is probably going to reshape how we solve the hardest problems on Earth. 14. Special relativity. In 1905, Albert Einstein introduced the idea that motion can stretch time and squeeze space, making them flexible depending on how fast you're moving. The rules of physics, he argued, look the same to anyone cruising along at a steady speed, whether you're on a train, a rocket, or standing still. One strange result is time dilation. Faster you go, the slower your clock ticks compared to someone who stays behind. If you spent a single day racing through space at nearly the speed of light, you could return to find almost a week had passed on Earth. Distances also contract in the direction of motion, so space itself warps for fast travelers. Einstein also gave us the iconic equation E equals mc squared, showing that mass and energy are two sides of the same coin. It sounds like an abstract idea, but the proof for it is everywhere, from nuclear power to GPS satellites, which literally need relativity corrections to tell you where you are. 13. General relativity. 10 years after he came up with special relativity, Einstein came back with something even bigger, a new way of thinking about gravity. Newton had described gravity as a kind of invisible force pulling objects together. Einstein argued it's not a pull at all, but the bending of space and time around massive objects. To give you a visual, imagine space-time as a stretched out fabric. Drop the sun on it, and the fabric dips. Planets roll along those curves not because the sun is pulling them, but because they're following the shape of that warped fabric. Even light bends as it passes near a star, tracing the same curves in the space-time cloth. General relativity gave us predictions that sounded unbelievable at the time. Clocks tick slower near strong gravity, light bends, and matter packed too tightly collapses into black holes. Every one of those has been confirmed, from the 1919 eclipse that showed starlight bending to the 2015 detection of gravitational waves. 12. Quantum mechanics. I've already touched on some of the ideas that grow out of quantum mechanics, like quantum computing and the search for quantum gravity. But this is the core theory itself. Quantum mechanics is basically the rulebook for the smallest pieces of nature, and it doesn't look anything like the everyday world we know. At the atomic scale, particles don't behave like tiny billiard balls. They can spread out like waves, shift between states, and only settle on one outcome when measured. That's why scientists talk in terms of probabilities instead of certainties. An electron isn't fixed in one spot until you look at it. It exists as a cloud of possibilities. Einstein resisted the idea and insisted that God does not play dice. That's a direct quote, by the way. But the experiments piled up, and the weird quantum world turned out to be the foundation for everything, from lasers to the smartphone chips we use today. 11. The Big Bang Theory. This is probably the most famous and controversial scientific theory in the world. We've all heard about it, and we all know what it says, more or less. The Big Bang Theory is our best explanation for how the universe began and why it looks the way it does today. According to the theory, about 13.8 billion years ago, everything, including matter, energy, space, and time, was packed into a state far smaller and hotter than anything we can picture. Then it began expanding. Space stretched, carrying galaxies with it, and that expansion has never stopped. The smoking gun is the cosmic microwave background, a faint glow of leftover light still filling the sky in every direction. It's the afterglow of the Big Bang, cooled over billions of years. The theory also correctly predicted that the universe would be full of hydrogen and helium, the simplest elements formed in the first minutes of existence. So when people talk about the Big Bang, they're really just talking about the start of the expansion we still see today. 10. The Standard Model of Particle Physics. If chemistry has the periodic table, physics has the Standard Model. It's the framework that lists the fundamental building blocks of the universe and how they interact, except for gravity. In this theory, all matter is built from just 12 particles, 6 quarks and 6 leptons, which include familiar ones like the electron. Then there are the force carriers, like photons for light, gluons for the strong nuclear force, and W and Z bosons for the weak force. Add the Higgs boson to the set, and you get a total of 17 particles that make up everything we can see and touch. The Standard Model has been tested to extreme precision. It predicted particles years before experiments confirmed them, and the discovery of the Higgs boson in 2012, which I will get to in a moment, was a huge milestone. Still, it's not the final word. It leaves out gravity and doesn't explain dark matter, so physicists know there's more to the story. 9. Higgs boson and the Higgs field. The Higgs boson really does solve one of physics' biggest puzzles: why particles have mass at all. The idea is that the universe is filled with an invisible energy field, the Higgs field. Particles moving through it interact in different ways. Some slip through almost untouched, like photons, which is why light has no mass. Others, like electrons and quarks, bump into the field more strongly, and that resistance shows up as mass. In everyday terms, it's like moving through molasses. The more you feel that drag, the heavier you are. The Higgs boson itself is a ripple of the field, and spotting it gave physicists the confirmation they'd been chasing for decades. When it finally showed up at CERN's Large Hadron Collider, it was the proof that particles really do get their mass from this invisible field, just as theory said they should. 8. Chaos theory. The butterfly effect. If you were around in the early 2000s, you probably saw that Ashton Kutcher movie, The Butterfly Effect. The title came from chaos theory, which is the science of how small changes can snowball into massive consequences. At its core, chaos theory says some systems are so sensitive to their starting point that even the tiniest difference can spin them off into completely different futures. The classic example is the butterfly flapping its wings, and weeks later, nudging a storm into existence. The idea first showed up in the 60s when meteorologist Edward Lorenz ran a weather simulation and rounded off a decimal. That tiny shortcut, just a fraction of a number, made his forecast veer in a totally new direction. Ever since, scientists have realized chaos shows up everywhere, in the climate, in ecosystems, in turbulence, and even in the motion of planets. The rules are still there, but the sensitivity makes long-term predictions almost impossible. 7. The cosmological multiverse. Think of the Big Bang as more than a one-time event. Some cosmologists argue that inflation, the rapid expansion that shaped our universe, may still be happening elsewhere. Each burst would create a new bubble of space-time, effectively a new universe sealed off from ours. These bubble universes might look nothing like what we know. Some could have stars and galaxies similar to ours, while others might follow entirely different laws of physics. In fact, string theory supports this idea, since its equations allow for a huge landscape of possible universes, each with its own unique rules. We can't see beyond our cosmic horizon, so direct evidence is lacking. Still, the multiverse helps explain one of the biggest puzzles in physics: why our universe seems so perfectly tuned for life. If there are countless universes out there, the odds that at least one could support us suddenly make sense. 6. Game theory. No, not the YouTube channel with Matt Pat, although enjoy your retirement, buddy. Just think. The math of strategy. It looks at situations where your best choice depends on what someone else decides to do. For example, poker, an auction, or even two countries in a standoff. Your move is only as good as your guess about what the other side's going to do. One of the best examples of game theory is something called the prisoner's dilemma. Two suspects are caught and questioned separately. If both stay quiet, they get light sentences. If one rats out the other, the snitch goes free while the partner takes the fall. If they both betray each other, they both get heavy sentences. Logically, the safe move is the first betrayal, but that could leave them worse off than if they had trusted each other. That tension between self-interest and group benefit shows up everywhere, in arms races, pollution agreements, and even workplace politics. So next time you weigh your options by asking, what are they going to do? You're already thinking in game theory terms. 5. Godel's incompleteness theorems. Godel's first theorem says that if you have a mathematical system strong enough to handle basic arithmetic, there will always be true statements inside it that cannot be proven using the system's own rules. It's like building the most airtight rulebook ever and still finding questions it can't answer. His second theorem was just as interesting. No such system can prove its own consistency. In other words, math cannot fully certify itself from within. When Godel published these results in 1931, mathematicians thought they were close to locking down math as a complete and flawless system. He proved them wrong. Nearly a century later, mathematicians are still stuck with the limits he uncovered. 4. Quantum entanglement and Bell's theorem. Two particles can be on opposite sides of the universe and still move in unison. Change one, and the other reacts instantly. Albert Einstein didn't like it at all. He called it spooky action at a distance, because it looked like the universe was breaking its own speed limit. For a while, people assumed that there had to be some hidden script the particles agreed on ahead of time, like cards marked before the shuffle. Then, in the 60s, physicist John Bell came up with a mathematical test to check if that was true. His inequality showed that if hidden codes existed, there'd be a statistical ceiling to the weirdness. When scientists ran the experiments, the particles blew straight past that ceiling. I guess this way instead. The message was clear. Entanglement is real. The real win, however, is that entanglement gives us tools that nature never meant to hand out, and scientists are already using entanglement to lock down data in ways that regular technologies can't touch. 3. The many worlds interpretation. As I mentioned a bit earlier, quantum physics has an awkward problem. Before you measure a particle, it exists as a cloud of possibilities. After you measure it, one outcome appears and the rest vanish. So what happens to all the other maybes? Physicist Hugh Everett had a radical answer. Nothing disappears. Every possible outcome plays out, just not in the same universe. Instead, reality splits. In one branch, the particle goes left, in another, it goes right. Apply this idea onto everyday life, and it means that there are endless versions of you out there, each living a slightly different story. Now, I know, it sounds like something Hollywood would come up with, but it's taken seriously because it removes the need for that mysterious collapse of the wave function. The catch is that we can't test it, since those parallel branches don't interact with ours. Still, the many worlds idea forces us to consider that every choice might come with a whole universe attached to it. 2. Dark matter. Look up at the night sky, and you're only seeing a tiny fraction of what's really there. Galaxies spin so fast that, by the math, they should tear themselves apart. But for some reason, they hold together. Something invisible is keeping them glued, and scientists call it dark matter. We can't see it, touch it, or shine light on it. It doesn't absorb or reflect, but its gravity gives it away. Light bends around galaxy clusters more than it should. Stars orbit faster than expected, and the large-scale structure of the universe only makes sense if a hidden mass is shaping it all. The big question is what it actually is. The leading idea is that dark matter is made of brand new particles with names like WIMPs or axions. Physicists have been chasing them for decades, but nothing concrete has emerged yet. 1. Dark energy. As baffling as dark matter is, dark energy leaves scientists with even bigger questions. In the late 90s, astronomers realized that the universe wasn't just expanding, but speeding up. To explain it, scientists decided there had to be some kind of hidden energy built into space itself. And the idea of dark energy was born. By our calculations, it makes up over 70% of the universe. The simplest version of the theory shows up in Einstein's own equations as a cosmological constant, a steady push that fills all of space. Another possible explanation is that it's the energy of the vacuum, the swirling background of empty space. No one knows the true answer, but its effect is obvious. For the last 5 billion years, dark energy has been in charge, driving cosmic expansion. So much so that in the far future, galaxies will drift so far apart that night skies could look empty. It's simply the biggest mystery we have in physics today. And that's a wrap. But before you click away, let's test your new science smarts. What's the difference between Einstein's theory of spatial relativity and his theory of general relativity? Is it A, motion versus gravity, B, nuclei versus galaxies, C, electricity versus magnetism, or D, sound versus light? Type your guess in the comments below, and while you're at it, tell me what science topic you'd like me to dig into next. Also, you have got to check out our related video, 25 science theories that are so strange they must be true. It's a list full of short, mind-bending scenarios that'll leave you stunned, second-guessing yourself, and questioning how you see the world. That link is about to pop up here any second now. And as always, like I said, thank you guys so much for watching. Like, share, comment, subscribe, do all that fun stuff. Really helps the channel. And I'll see you guys next time.